Hello, and the series is continuing. And, we have already solved some of the questions, and I think this is the fourth question that I am going to solve. Related to the this question is related to the black body radiation, and we have just started the series in which the we are discussing about the questions of the quantum mechanics. And this question in the fourth question in the radiation emitted by the black body, the ratio of the spectral density at the frequency will varies with the mu as okay. And simply they are asking the ratio of the spectral density. For this, we should know already the formula for the spectral density depend upon the frequency and the temperature T, and it is nothing but the some constant. Because I am not taking the constant because there is some ratio we are going to take, and there is h mu, and then divided by e to power h mu by kt minus 1 black body radiation spectral density formula for the black body radiation. And let's suppose I have taken the for the mu frequency, and for the frequency 2 mu it become, and the temperature they are not talking about, then we will take the temperature as a constant. And the other is the some constant term, and h 2 mu divided by e the power h2 mu by kt minus 1. That's it. And we are going to take the ratio. Uh, okay, they are talking about the frequency 2 mu by, then we take, I will take the frequency 2 mu in the upper, and 2 mu by t to the 2 mu by t. We are simply taking the ratio, and 2h 2h mu divided by e the power minus h 2 mu by kt minus 1. And and the other term is going to be, the other term is going to be reciprocal, then we simply reciprocal it, then we will get, I think, e to power h mu by kt minus 1 and divided by h mu. That's it. And after some of the factors will cancel out, and then we are going to use a one property. Let me generate some space here, and then I think we are going to use the property a square minus b square is equal to a square minus a square minus b square is equal to a minus b a plus b. Simple that formula, and we are applying here at the denominator. For this, then we will get the value 2 into the above expression is same, and minus 1, and then in the below, if we use the property a minus b is simply h minus h mu by kt minus 1, and other is e h mu by kt plus 1. And then this one term is going to cancel out, this term whole term is going to cancel out, and then we will remain with the value 2 into, and in the denominator, it come out to be with the negative power, with the negative 1 power, and then it become minus 1. Then you can check out the options. I think the option is B is matching with it. Yes. And the other next questions, let me take the next question. Next question is the gamma photon emitted from the cesium, and they are providing the mass number also. The source collided with an electron at the rest. Okay, if the Compton shift of the photon is given to you, and then the scattered angle is close to. Okay, simply for the Compton shift, that Compton wavelength shift. How much wavelength shift? And for this, you have to know the formula. It is simple. Change in the wavelength uh, is equal to h mu naught by c is equal to 1 minus cos theta. Uh, Here h lambda dash is the wavelength of the uh, wavelength of the scattered photon. Wavelength of the this lambda is the wavelength of the incident photon. H is the Planck constant. M naught is the rest mass of the electron. Okay, remember it. That's very important. And c is the speed of light. And the Compton wavelength is depend upon the theta only. Only theta is responsible. If you change the theta, then the Compton wavelength is going to shift. It does not depend upon the intensity of the photon, and it depend upon the theta only. And for this, the in the question they are providing the Compton shift. This Compton shift is already provided to you, and this is nothing but 2 into 10 the power minus 13 meter, and h and these values are already given to you. Just put the values all, and you will get the cos theta value. And I think the answer B is matching. When you try to get the theta is, I think B, just check it out, and you will get the directly uh, theta from it, from this expression. The simple question for the Compton effect. And let me do the other question. Yeah, in this question, photoelectric effect. This is the question now. The photoelectric effect, uh, and in photoelectrons experiment, both the sodium and the tungsten, their work function are already given to you, and metal are illuminated by the ultraviolet light of the same wavelength. Okay, they are incidenting the same wavelength, so ultraviolet rays on the sodium and the tungsten. Their work function are different, and if the stopping potential of the tungsten is measured to be, stopping potential is given to you, and they are then the value of the stopping potential of the sodium they are asking. Okay, for this we know that the energy is, the incident energy is going to be divided into two things: the work function, and the rest of the energy remaining goes to the kinetic energy, that provide the kinetic energy to the electron. To the electron, yes. And okay, and they are the two cases of the sodium. Let's suppose I make the case for the sodium. Let's suppose the because the incident energy is for the both cases are equal, and let's suppose the sodium wave function, let us phi sodium s, the s, and kinetic energy is going to be ks. Okay, and h mu, and the other relation for the tungsten is I think the phi t plus ke, kinetic energy of the electron for the case of the tungsten. Yes, And we know that the kinetic energy is nothing but the kinetic energy, if we relate to the stopping potential, because the stopping potential values are given to you, it is nothing but E value is electron charge. E value is 1.6 into 10 to the power minus 19 coulomb, and V is the stopping potential. And simply, if we replace this Ke with the respective stopping potential, then we will get the relation. Then we get the relation phi s plus E stopping potential of the in the case of the sodium, and the is equal to stop work function of the tungsten plus stopping potential of the tungsten. And then when we equate these one and two expression, I think there is one unknown. The tungsten for the tungsten what they are already given. The sodium case they are asking, if we will equate this, you will get the value simply. And thank you for this. And yes, and can I give you the one more question to solve it? Yes, you can try it yourself. The fourth question, and if you are not getting, we will discuss in the next video lecture. Okay, thank you. Have a nice day.